Okay, so I hope I am audible to all the students attending the lecture today. Um, this is the first unit in semester 4 micro, and this is called as the general equilibrium and welfare. Okay, so we'll be starting with this lecture today. And the first thing we are doing within general equilibrium is the concept of exchange. Now, recall that in micro semester 3, we had talked about one consumer. There were two goods, X1 and X2. And if you remember, the consumer was endowed with endowments omega 1 and omega 2. Okay. Whatever analysis we had done in semester 3 was called as the partial equilibrium analysis. This means that there was one consumer, and in one particular market, we were trying to achieve equilibrium using demand and supply. But now what will be different here? Now in this semester, we will be studying the general equilibrium analysis. Now in general equilibrium analysis, there will be more than one consumer, more than one market, and we will achieve equilibrium in every market. Okay, so now when there was only one consumer and two goods, our diagram used to be a two-dimensional diagram, and we used to draw indifference curves and budget lines, if you remember. But now in general equilibrium analysis, the tool we use is called the Edgeworth box. This will actually help us in understanding the concept of exchange. Okay, so let me come to the whiteboard. Let us understand what is exactly meant by Edgeworth box and how we can use it as a tool to understand the concept of exchange. Okay, so what is Edgeworth box? Edgeworth box is a graphical tool that can be used to analyze the exchange of goods. It can be used to analyze the exchange of two goods between two people. Okay, so Edgeworth box is a graphical tool which can be used to analyze the exchange of two goods between two people. Now let's get deeper into it. So suppose there are two consumers. Suppose there are two consumers, or let's call them as agents, named A and B. Okay, and there are two goods. There are two goods, 1 and 2. So suppose my A's consumption bundle is given by the vector XA, which is X1A and X2A. Now what is X1A? X1A denotes the amount of good 1 consumed by agent A. X2A denotes the amount of good 2 consumed by agent A. Similarly, B's consumption bundle will be given by the vector XB, which is X1B and X2B. Now, what is X1B? Amount of good one consumed by agent B. And what is X2B? Amount of good 2 consumed by agent B. So these are my consumption bundles for agent A and agent B. Now, what is meant by an allocation? What is meant by an allocation? An allocation is nothing but set of all consumption bundles. So an allocation X is nothing but set of consumption bundle of agent A and consumption bundle of agent B. And when is an allocation said to be feasible? So feasible allocation. Our next heading is feasible allocation. An allocation is said to be feasible if the total amount of each good consumed, if the total amount of each good consumed is equal to the total amount available. Is equal to the total amount available. That is, total amount of good one consumed by agent A and B is equal to the total amount of good one available in the economy. Now, what is the total amount of good one available in the economy? Total amount of good one which A is endowed with plus total amount of good one which B is endowed with. These are my endowment vectors. Okay, so I can write it like this. I can write that A's consumption bundle is this and A's endowment bundle. These are my endowment vectors or my endowment bundles. Now, agent A's endowment bundle is this is omega 1A and omega 2A, and agent B's endowment bundle is omega 1B and omega 2B. So agent A is born with how much amount of good one? This much. And agent A is born with how much amount of good 2? Omega 2A. Similarly, agent B is born with how much amount of good one? Omega 1B. And agent B has how much amount of good 2? Omega 2B. So, an allocation is said to be feasible if total amount of each good consumed. Now, if I talk about good 1, this is total amount of good 1 consumed by A, total amount of good 1 consumed by B is equal to total amount of good 1 available in the economy. Now, what is the total amount of good 1 available in the economy? Total amount of good 1 available with A plus total amount of good 1 available with B. Similarly, I can do the same analysis for good 2. So for good 2, total amount of good 2 consumed by agents A and B should be equal to total amount of good 2 available in the economy. Total amount of good 2 consumed by agents A and B should be equal to total amount of good 2 available in the economy. So I hope all students are clear. We have started with the general equilibrium analysis today, and we are studying the concept of exchange, and to understand it, the tool we use is called the Edgeworth box. Now, to understand the Edgeworth box, we need to introduce some vectors. You can see on your screen that there are two agents A and B, two goods 1 and 2. A's consumption bundle is XA, which is X1A, X2A. B's consumption bundle is capital XB, which is X1B, X2B. Their endowment bundles are as follows. Omega A is omega 1A, omega 2A, and omega B is omega 1B, omega 2B. And allocation is nothing but the set of consumption vectors XA, XB. And when is an allocation said to be feasible? It is said to be feasible if the total amount of each good consumed is exactly equal to the total amount available in the economy. So total amount of good one consumed by both agents A and B should be equal to total amount of good one available in the economy, which is omega 1A plus omega 1B, and total amount of good 2 consumed by agents A and B should be equal to total amount of good 2 available in the economy, which is omega 2A plus omega 2B. So now we are in a position to draw the Edgeworth box. So I hope till here no student has any doubt. If you have a doubt, you can feel free to unmute your mic and ask. Okay. Okay, now let's draw the Edgeworth box. Let us see how the Edgeworth box looks like. Okay, so an Edgeworth box is nothing but a rectangle. Now there are two agents A and B, so we'll have two origins. You can see origin of agent A. Agent A is x-axis and agent A is y-axis. Similarly, origin of agent B. Origin of agent B, agent B's x-axis and agent B's y-axis. Now, when I am plotting from agent A's axis, this is my origin. This is my amount of good one available in the economy, measured in this direction. And my amount of good two available in the economy from A's origin is measured in this direction. But when I talk about agent B, agent B's origin is this. So you need to turn your registers to agent B's origin. Now from agent B's origin, this is my good one available, good one in the economy. So from agent B's origin, it is measured towards the left, and from agent B's origin, good 2 is measured down. It is measured downwards. So it's very simple. When you are plotting the Edgeworth box, you need to see how you are measuring goods and with respect to whose origin. So this is agent A's origin. This is agent B's origin. From agent A's origin, this is good one is measured on the horizontal axis from left to right. Good 2 is measured on the vertical axis like this, upwards. From agent B's origin, good one is measured towards the left in this direction, and good 2 is measured downwards. Now I can choose a point in the Edgeworth box known as omega. Suppose this is my point in the Edgeworth box. Clearly, this denotes omega 1A, amount of good one which agent A is endowed with. This point will denote omega 2A, amount of good 2 which agent A is endowed with. This will denote omega 1B, amount of good one agent B is endowed with. and this will denote omega 2B, amount of good to agent B is endowed with. So you can see one point in the Edgeworth box represents four particular values: omega 1A, omega 2A on the A's axis, and omega 1B, omega 2B on the B's axis. Okay, the next thing you can see is, suppose my indifference curves are in this particular order. Suppose we talk about convex preferences, and suppose our indifference curves are convex to the origin. How will A's indifference curves look like? A's indifference curves will be like this, convex to the origin from A's axis, and I can draw a lot of indifference curves. Obviously, one particular indifference curve will pass through the endowment also. These are my A's indifference curves. It's a family of A's indifference curves, right? And similarly, how will I draw B's indifference curves? Now, B's indifference curves, you will turn to the B's origin. So turn your register to B's origin. So from B's origin, suppose B also has convex ICs, then from B's origin, the ICs will look like this. Somewhat like this, dotted. B's ICs I am drawing dotted, A's ICs are solid. So from B's origin, the indifference curves are going to look like this. Again, I have drawn a family of indifference curves. So A's indifference curves are solid ICs, and B's indifference curves are dotted ICs. Okay, what can you see? A's indifference curves are increasing in which direction? A's indifference curves, in case of A's indifference curves, utility increases in the north east direction. It's northeast. You can see the northeast direction. You're moving towards the north and east. Whereas B's IC, in case of B's indifference curves, B's utility is increasing in which direction? B's utility is increasing in the southwest direction. So you can see B's indifference curves, utility is increasing as we move in the southwest direction. As we move in the southwest direction, B's utility or B's satisfaction is increasing. As we move in the northeast direction, A's utility or A's satisfaction is increasing. So far, I hope it's clear to everyone. I hope no one has any doubts. Okay, then I can choose, just as I have chosen a particular endowment bundle, I can randomly choose a consumption bundle in the Edgeworth box. Suppose this is my allocation X. So what will this point denote? Now this is something, the X allocation right now I have chosen randomly. But later in this chapter, we will find out how to find this allocation. Right now, I have just chosen it randomly. Suppose my allocation is this, which is X. So this will denote X1A, which is amount of good one consumed by agent A. Okay. This will be X2A, amount of good to consumed by agent A. This will be X1B, amount of good one consumed by agent B, and this will be X2B, which is amount of good to consumed by agent B. Clearly, what can we see? If I talk about agent A and B, if I talk about agent A, So you can see that A is a, if you remember the buying and selling chapter from semester 3 of micro, you can recall that agent A is consuming less than his endowment. What is agent 1? Agent A's endowment is omega 1A. But how much is agent A actually consuming? X1A. So I can say that agent A is a net seller of good 1. Agent A is a net seller of good 1 because he is consuming less than his endowment. Look at agent B. Sorry, if I look at agent A only, so agent A is a net seller of good 1, and look at good 2. Agent A is consuming more than his endowment of good 2. Agent A's endowment of good 2 is this much, but how much is he actually consuming? This much. So I can say agent A is a net buyer of good 1. So why is agent A a net seller of good 1? Because he is consuming less than his endowment. Why is agent A a net buyer of good 1? Because he is consuming more than his endowment. Let's look at agent B. If you look at agent B, now turn to B's origin. To understand in depth, turn to B's origin. You will see that agent B is consuming more than his endowment of good 1. And on the vertical axis, agent B is consuming less than his endowment of good 2. So if I talk about agent B is a net buyer of good 1. Why is agent B a net buyer of good 1? Because she is consuming more than her endowment. And she is a net seller of good 2. This is good 2, guys. I'm correcting it. This is good 2. Agent B is a net seller of good 2. Why is she a net seller of good 2? Because on the good 2 axis, she is consuming less than her endowment. Now you will understand this only when you actually turn your registers to B's origin. If you look at B from here, you will make a mistake. You turn your registers to B's origin. Then you will see that B is consuming more than her endowment of good 1. So she is a net buyer of good 1. And she is consuming less than her endowment of good 2. So she is a net seller of good 2. So I hope all students have understood the Edgeworth box analysis. I hope you have understood how to plot the Edgeworth box. In case anyone has any doubt, please feel free to ask. Okay. Now let's turn to a very important concept in this course called as Pareto efficient allocation. Pareto efficient allocations. Okay, so let's talk about what is actually meant by Pareto efficient allocations. Now to understand this concept, let us first take an example. So suppose there are two consumers. Suppose there are two consumers, A and B, and suppose both these consumers have a Cobb-Douglas utility function. So utility function of agent A is x1A, x2A, and utility function of agent B is x1B, x2B. Both the agents have a Cobb-Douglas utility function. The subscripts denote the agent and the superscripts denote the goods. Okay, now it's given, suppose suppose total amount of X1 available in the economy. Suppose total amount of X1 available in the economy is 8 units and the total amount of X2 available in the economy, total amount of X2 available in the economy is how many units? Suppose it's 10 units. All this is given to us in the question. Also, suppose A's endowment is given to us as 5,2. A has 5 units of good 1 and 2 units of good 2. And suppose endowment of agent B is, how much will endowment of agent B be? We know that total amount of good 1 available in the economy is 8 and total amount of good 2 available in the economy is 10. If the total amount of good 1 available in the economy is 8 and A has 5 units, how much will B have? 3 units. And if total amount of good 2 available in the economy is 10 units and A has 2 units, how much will agent B have? 8 units. Okay, so we can plot this in the Edgeworth box. So all of you focus on the diagram I am drawing. Okay, now the length of the Edgeworth box denotes the total amount of good 1 available in the economy and the breadth of the Edgeworth box denotes total amount of good 2 available in the economy. So using our registers, I can draw a line of length around 8 centimeters. This will be my A's origin and the breadth will be a line of 10 centimeters. Okay, so this is my Edgeworth box. This is A's origin. This is B's origin. Okay, this is my B's origin. Now from A's origin, this is how much? This is 8 from A's origin. From A's origin, this is 8 and this is 10 because my horizontal axis denotes the amount of good 1 available in the economy and vertical axis denotes the amount of good 2 available in the economy. So from A's origin, this is 8 and this is 10. But if you turn to B's origin, if you look at B's origin, from B's origin, this is 8. From B's origin, this is 8. And from B's origin, this will be 10. Or I can write it like this to make more sense. After the slash, it denotes B. So from A's origin, this is 10. But from B's origin, it denotes 8. Similarly, from A's origin, here we have 8. But from B's origin, we have 10. Now, you will be able to understand this again only when you turn to B's origin. From B's origin, when you mark, this will be 10, but this will be 8. Okay, and now let's denote the endowments. The endowments are 5,2. So where will 5 lie? This is 8. This is 4. So 5 will be somewhere here. This will be 5. And where will 2 lie? This is 10. So this is 5. If this is 5, 2 will be somewhere here. So this is 5. This is 2. From B's origin, from A's origin, if this is 5, then from B's origin, this is how much? This is 3 from B's origin. And from B's origin, if this is 2, then from B's origin, this is how much? 8. So you can see I have drawn the endowment allocation. 5 and 2, 3 and 8. From A's origin, this is 2 and this is 5. From B's origin, this is 3 and this is 8. You can see that 5 plus 3 sum up to 8 and 2 plus 8 will sum up to 10. So I hope things are becoming clear to students. Any doubt, please unmute your mic and ask. In case any student has any doubt, please feel free to unmute your mic and ask. Okay, now suppose both the agents are consuming their endowments. So I can draw A's IC. Now A's IC is like this. This is IC of A, and suppose B's IC is like this. Both are currently consuming their endowments. This is ICB, the dotted one, and both the agents are consuming their endowments. I haven't introduced budget lines, and in this topic, we need not worry about the budget lines. When we are doing the concept of Pareto efficient allocations, we are not concerned with the budget line. We are only concerned with trade right now, exchange right now. And I am saying, suppose the agents are consuming their endowments. Suppose. Then I want to ask you, if both A and B consume their endowments, if both A and B consume their endowments, what is the utility A will get? The utility A will get will be x1A into x2A, which means 5 into 2, 5 into 2, which is 10. What is the utility B will get? The utility which B will get will be 3 into 8, which is 24. Remember, the utility functions are Cobb-Douglas. Now let us see, suppose they trade with each other, can they become better off? Like, should they trade with each other? So look at this. Suppose B gives 1 unit of x2 to A in exchange for 1 unit of x1 from A. Let us look at this trade. Suppose B gives 1 unit of x2 to A, and in exchange B gets 1 unit of x1 from A. So now I ask you, what will my new utility be? So for first of all, what will be my new allocation? What will be my new allocation? A will now have how much? A has 5, 2. A gets 1 unit here, but then A gives 1 unit here to B. So it's going to be 4, 3. For B, B gets 1 unit here, but then B gives 1 unit here. So you can see this trade is happening. B gives 1 unit of x2 to A. That means 8 से 7 हो जाएगा और 2 से 3 हो जाएगा. And A gives 1 unit of x1 to B. So यहाँ पे 4 हो जाएगा और यहाँ पे भी 4 हो जाएगा. Now let us see what the utilities will be. Now A's utility will be 4 into 3, which is 12, and B's utility will be 4 into 7, which is 28. You can see both A and B have become better off. Initially A's utility was 10, now it has increased to 12. Initially B's utility was 24, now it has increased to 28. So you can see, therefore, both A and B have become better off. Both A and B have become better off. That means they should trade. Where have they reached? If you look at in the diagram, this is 4 and this will be 3. And you can see this point will be 4, and this point from B's origin will be 7. So you can see A has also gone to a higher IC. This point is omega dash. A has also gone to a higher IC from A's origin, and you can look at B also. Look at B's IC from B's origin. B has also gone to a higher IC. See what I am drawing? This point is omega dash. This point is omega dash. A has also gone to a higher IC. B has also gone to a higher IC. That means that by trading this particular scheme, both A and B have gone to higher ICs from their respective origins. A has also become better off, 12 is more than 10. B has also become better off, 28 is more than 24. So I want to ask, they will keep trading, but when will they stop? The question is, they'll continue to trade, but then when will they stop? When will they stop trading with each other? So that is our next question. So they will stop trading with each other when both the ICs will exactly become tangent to each other. You can see A's ICs are going up, B's ICs are going down. A's ICs are going towards this region, B's ICs are going in this region. They'll stop when both the ICs will become tangent to each other. So I can write it. Let me clear this off. Therefore, both agents A and B will continue to trade with each other both agents A and B will continue to trade with each other till the point when their ICs become tangent to each other. They will continue to trade with each other till the point when both their ICs become tangent to each other. This point of tangency is called the point of Pareto efficiency. This point of tangency is called the point of Pareto efficiency. Okay, so I can erase the diagram and I can show when will they stop. When will they stop trading with each other? They will stop trading with each other when eventually their ICs, I can erase all this right now, we don't need all this. They'll stop trading with each other until they reach a point when A's IC becomes exactly tangent to the B's IC. This point of tangency, this is my point of tangency, and it is called the point of Pareto efficiency. This point is called the point of Pareto efficiency. So once both the agents have reached this point, now they will not trade. Because now if they trade, one agent will become better off by making the other agent worse off. This is my point of Pareto efficiency, point P. No agent will want to deviate from point B. They will keep on trading with each other until they reach point B. But once they have reached point B, now they will not trade further. Because now if they trade, one agent will become better off by making the other agent worse off. Now mathematically, how will I find this condition mathematically? So let me erase some portion for you. We have understood all this, so let me erase this for us. Let us now understand mathematically. Diagrammatically, you guys have understood what is the point of Pareto efficiency. Now mathematically, what is the point of Pareto efficiency? Okay, so mathematically, when I say that two ICs are tangent to each other, what does this mean? When I say that two ICs are tangent to each other, slope of agent A's IC, which we call as MRSA, should exactly be equal to slope of agent B's IC, which we call as MRSB. Now, all of you know how to find MRSA. MRSA is nothing but del UA by del X1A divided by del UA by del X2A. Remember, MU marginal utility of one good upon marginal utility of another good. Similarly, MRSB will be del UB by del X1B upon del UB by del X2B. So now you can see what will del UA by del X1, if I differentiate this utility function with respect to X1A, what do I get? If I differentiate this function with respect to X1A, I finally get what? I get X2A. And if I differentiate the utility function of agent A with respect to X2A, what do I get? I get X1A. I get X1A. Similarly, if I differentiate the utility function of agent B with respect to X1B, what do I get? I get X1B. And if I differentiate the utility function of agent B with respect to X2B, what do I get? I get X2B in the numerator. If I differentiate the function with respect to X1B, and in the denominator, if I differentiate the function with respect to X2B, I'll get X1B. This is what I'll get. This implies that X2. Okay, another thing, this is one condition I have got. This is one condition. Another condition is that total amount of good one consumed by both the agents should be equal to, what's the total amount of good one available in the economy? 8. And total amount of good 2 consumed by both the agents should be equal to total amount of good 2 available in the economy, which is 10. So look at it from equation 1. I can write equation 1 like this. X2A by X1A is equal to X2B, I can write as 10 minus X2A upon X1B, I can write as 8 minus X1A. This I am writing using equation 2 and equation 3. This is my equation 2. This is my equation 2 and this is my equation 3. So from 2 and 3, I can write X2A by X1A as 10 minus X2A upon 8 minus X1A. If I cross multiply, X2A into 8 minus X1A is equal to 10 minus X2A into X1A. And if I further solve it, how it's going to look like? Let me make some space first. This is 8 and this is 10. Okay, so this becomes 8 X2A minus X1A X2A is equal to 10 X1A minus X1A X2A. This and this cancels. So we get 8 X2A is equal to 10 X1A, or I can write X1A upon X2A is equal to 10 by 8, and X1A by X2A itself is also equal to X1B by X2B. and this is 2 4s are 2 5s are. That means the allocation will be Pareto efficient if both the agents are consuming goods in the ratio of 5:4. So this is my answer mathematically. So graphically, what's the point of Pareto efficiency in this question? In this question, graphically, the point of Pareto efficiency is when both the ICs become tangent to each other. Once they reach this point, they will stop trading. Mathematically, what's the point of Pareto efficiency? Mathematically, the point of Pareto efficiency is when MRS of A is equal to MRS of B. This is the MRS of A. This is the MRS of B. At the same time, we are given the feasibility conditions. Total amount of good 1 available is 8. Total amount of good 2 available is 10. So I can write x2a by x1a as x2b is 10 minus x2a and x1b is 8 minus x1a. Cross multiplying and solving, we get x1a by x2a as 10 by 8, which is 5 by 4. And from this equation, from equation 1, x1a by x2a is equal to x1b by x2b. Okay, from this equation, what I can write is, I can take reciprocal. x1a by x2a is exactly equal to x1b by x2b, just taking the reciprocal of equation 1. That means x1a by x2a is equal to x1b by x2b is equal to 10 by 8, which is 5 by 4. That means both the agents will consume the goods in the ratio of 5:4. This will be the point of Pareto efficiency mathematically. Okay, this will be the point of Pareto efficiency mathematically. So I can finally write now, erasing all this. I hope no student has any doubt. If you have a doubt, you can unmute your mic and ask. Okay, so, okay guys, this was one Pareto efficient point. Now this was one Pareto efficient point when I had one particular endowment. When I had one particular distribution of endowments, but for different endowments, I can have different Pareto efficient points. So you get one Pareto efficient point for one particular distribution of endowments between A and B. But for different distribution of endowments, I can get different Pareto efficient points. So this is A's IC. Okay, these are A's IC. And these are B's IC, the dotted ones I am drawing on the screen. These are all B's ICs. Now, if I join, now these are all Pareto efficient points. For one particular distribution of endowments, for one particular distribution, of endowments between A and B, we get one Pareto efficient point. Okay, we get one Pareto efficient point. But for different distribution of endowments, for different distribution of endowments between A and B, we get different Pareto efficient points. We get different Pareto efficient points. Now, when we join all these Pareto efficient points, when we join all these possible Pareto efficient points with the origin of A and origin of B, we get something called as the contract curve. We get something called as the contract curve. So contract curve is the locus of all the Pareto efficient points. So every point on the contract curve represents a Pareto efficient allocation. Every point on the contract curve represents a Pareto efficient allocation. I have just drawn 3, but all these points are eventually Pareto efficient allocations. Every particular point on the contract curve is a Pareto efficient allocation. And remember, you will get one Pareto efficient allocation for one possible distribution of endowments. आप endowments को A और B के बीच में जैसे जैसे आप change करते चले जाओगे distribution उनकी, you will keep on getting different Pareto efficient points. Okay, so the last thing after which we end the lecture, okay, what is the summing up of Pareto efficiency? So summing up an allocation is said to be Pareto efficient if point 1, there is no way to make all the people involved better off. There is no way to make all the people involved better off. Second, there is no way to make some individual better off without making someone else worse off. Okay. Third point, all gains from trade have been exhausted. All gains from trade have been exhausted. And the last point, there are no mutually advantageous gains from trade to be made. There are no mutually advantageous gains from trade to be made. So we say that an allocation is said to be Pareto efficient if there is no way to make all the people involved better off. There is no way to make some individual better off without making someone else worse off. All gains from trade have been exhausted and no mutually advantageous gains from trade are to be made. That means once you reach the point of Pareto efficiency, you will not want to deviate from that point. That means आप ट्रेड तब तक करोगे जब तक आप Pareto efficient point पे पहुंच नहीं जाते. बट एक बार आप Pareto efficient point पे पहुंच गए, एक बार दोनों एजेंट्स Pareto efficient point पे पहुंच गए, उसके बाद वो ट्रेड नहीं करना चाहेंगे, बिकॉज उनको पता है कि Pareto efficient point पे पहुंचने के बाद अगर हमने और ट्रेड करी तो one of them will become better off by making the other one worse off. One of them will become better off, but other party will become worse off. So they will not trade. Once they reach the Pareto efficient allocation, they will stop trade. Okay. So I hope all students have enjoyed this concept today. Okay. Anyone has any doubts, feel free to unmute your mic and ask, or you can give me a call. You know my number, or you can email me at divineschoolofeconomics@gmail.com for further doubts. Okay. This is where I stop the lecture today.